Let us now talk about the important concept of memory stack. The memory stack, or the stack memory, is a memory usage from your main memory that is used to temporarily store data. It is mainly used to store registers, and it does use a concept of a first in, last out buffer. So when you put data, if you keep stacking on that, you will increase your stack, and when you'll retrieve data, you will start from the last one that entered your stack, and you'll end up finishing with the first one you did put on your stack. The Cortex-M is using the concept of a full descending stack model. What does that mean? It means that you start storing or stacking data into your memory stack from the memory address that is the highest. And then you keep going down in your memory organization. So you'll start at address, for instance, 100, and then you will write at the next time at address 96, and so on and so forth. The operation to store and retrieve data from the memory stacks are called the push and pop operation respectively. Finally, the stack pointer, also known as register 13 in your memory organization for your Cortex-M architecture, stores the address of the current location of your stack. So the next available space will be this location minus 4 forward push. Now, how does this push and pop operation work? Let us look at the mechanism of storing a register through a push operation. So first of all, here's a register that we want to save. The memory address is going up, as this is our memory address space, and the stack pointer points to this location, which is the last used location on our stack. The push operation is going to save the content of this register to the next address location available in the memory address going downwards. So after a push operation, you will end up having the content of your register saved in that location, and now your stack pointer is going to point to that new location. Once you have pushed some data, you can have some data processing, meaning that the original content of your register is going to get destroyed. And after you're done with that, you might want to retrieve the initial value of this register. So it's like, again, a temporary store of your operations. And in order to do that, you will run the pop instruction. What does a pop instruction do? The pop instruction takes the data currently located or pointed by the stack pointer, take this data and restore that in the register. Then it increments the stack pointer. Remember that it increments it since we are using a downwards stack model. And as a result, the stack pointer always points to the last location used in your stack memory. Once you're there, you have been able to restore the content of your register. So the bottom line is that the push and pop operation and the memory stack are used to temporarily save the content of a register, and that's what we're going to use in most cases, such as the interrupt controllers and handlers. Now, why does the stack grow downwards? This is to allow maximum flexibility. If you look at a given piece of memory, and if you remember your C class or programming classes, we basically have 3 ways to use a memory. The first option is to have a static data allocation. So it's when you write a given variable int x, x is going to be saved somewhere in the memory at a reserved location. And this static data allocation is done at the lowest address in your address space. On top of that, in order to have more dynamic flexibility, you have 2 mechanisms. You have the heap and the stack. The heap is where you will store your dynamically allocated data. So when you run a malloc in C, the data will go in that space. And this memory is growing upwards. So the more malloc you do, the higher it goes in that direction. Now, in addition to that mechanism, we have this stack concept, which, as I said, is used for temporary data storage. And this stack starts at the highest possible memory address and grows downwards as much as you use it. So the bottom line is that by using these 2 mechanisms for upward growth and downward growth gives you the maximum flexibility so you can minimize the amount of free memory space you have in between. However, on a side note, I already told you in class that it's very dangerous to use dynamic data allocation for embedded systems. The reason is that you don't have the full mechanisms of what an operating system will implement: garbage collector, segfault, mechanisms management, and so on and so forth. So you open the door to a lot more problems when you use dynamic data allocation rather than using static data allocation and passing data through pointers, for instance.